So in this video, we're going to continue thinking about chromatograms. So those, graphs, there we go, where we have peaks representing each component of a mixture that have retention times. And then whatever the detected response is, could be a lot of things, but it would just be whatever the instrument is measuring. So in the previous video, I mentioned that the more narrow the peak, the better. That we have better resolution. If they're narrow, that's the gap. It goes all the way down to the bottom before another peak happens. And so broad peaks like this one's not that broad, but this one's right here is pretty broad, is not ideal. So we're gonna look at how why are some of them narrow? Why are some of them not? What are the circumstances that go into that? So diffusion, which is the equilibrium process of the solute between the mobile and the stationary phases. What that means is when you've got, let's say we have two components in a mixture. They go through the chromatography and they separate from each other, but then there's more than one molecule of each component. So you might have, 0.5 moles of the one compound. So it makes a band, kind of like which was demonstrated earlier in the chapter. And so as it moves down, they move together because they're all the same compound, so they all have the same interactions. But they will this diffusion is that they slowly start to seep away from each other. So I'll show you a picture on the next slide of that. But longitudinal diffusion is that the solute molecules, as they move down the column, they've already separated from the other chemicals, but the solute molecules of the same compound are slowly moving away from the center of the band. And there's nothing we can do about this. This just happens. The longer the column, the more that this is going to happen. So this kind of shows us this. This is at the top of the column. All that compound makes that line. Okay. And as we move down, it kind of starts seeping out. It's spreading out. And then as it goes further and further, that's happening. And you can see down at the bottom, this image, and this image is what the peak would look like in each of those situations. So as that band gets wider, the peak gets wider. So we have to, we'd rather have this than this, because now we've got the resolution. Now we've got a very clear retention time. It's just better. Okay, it's easier to or it's not easier, but more accurate with the area under the curve. So we just see that this happens. This just happens. Okay, naturally. So how can we try to fix this? Well, the flow rate of the column, which is how much pressure is being pushed on the mobile phase. So if it's a gas, that's a thing that we actually have the pressure in, like atmospheres. And if it's a liquid, the instrument can push pressure. When we did think about the thin layer chromatography, there's atmospheric pressure is all that was happening with that because it was just sitting out. Okay, but if the flow rate of the column increases, so we're shoving the sample through the column faster, that will decrease the diffusion because they don't have as much time to spread out. So the faster the flow rate, the less diffusion that we have, which means we have sharper peaks. Okay. So if we want to decrease the diffusion, we could increase the flow rate. Now, just while we're talking about this, everything we do has a positive and a negative with this chromatography stuff. So increasing the flow rate gives us sharper peaks, decreases the diffusion, but what it does is doesn't give the mixture very much time to separate, so we might not see very good resolution. The chemicals aren't able to move away from each other. So we're going to look at looking at this diffusion. Okay, one cause of this diffusion is when we have packed columns. So this image, each of those squiggly things is stationary phase. So think like the sand shoved in the burette. Okay. So just as our samples moves through the packed column, what this is trying to show is molecule 1, molecule 2, and molecule 3 are all molecules of the same compound. So they would have the same intermolecular forces. So, how the time it takes to move through the column should technically be the same because it has the same interactions. Well, you can see here that when we have a packed column, that's not necessarily the case. And that's all because of the little solid pieces that are the stationary phase. If they're not all identically sized, if their shape and size are different, then the amount of time it takes for them to move through the column varies a little bit based on like the literal path they have to take, who they're dodging, what they have to go around. So molecule number 3 showed up, it didn't leave the column until later. Molecule number 1 left the column fastest because it didn't have anything in its way, and molecule 2 was somewhere in between. So this is another issue with diffusion, like one of the reasons behind diffusion. And this one, the only way around that is to try to make sure that your column stationary phase are as identical, like the little pieces are as identical as possible. So the Van Deemter equation is what is going to take into account the broadening of a peak. So this looks at all the situations that that can happen. So the multiple paths is represented by the capital letter A. Longitudinal diffusion is represented by the B over UX, and the CUX is the equilibration time, which is just how long it takes for the component to interact with the mobile phase and the stationary phase. That's different for every compound. If it's a slow equilibrium, then that's going to slow down the process. So the A, B, and C values are constants that are based on the column. So it's not like it's a constant that we see all the time. It's unique to the column. It's unique to the stationary phase and mobile phase being used by that column, and it's unique to the temperature. So the Van Deemter equation is looking at this broadening of peaks. So these are the 3 reasons why peaks are broadened. You're not going to be actually calculating with the Van Deemter equation. I really wanted to show it to you so you understand. It's like, well, why do peaks get broader? Well, these are the 3 answers. Okay, and so what can we do? So in order to have good separation, the elution time, the time between the peaks, is an important way to determine if the compounds are separated and how broad the peaks are. So these are the situations we're looking for. We want good separation, the elution time between the peaks, which is that resolution. And then we want the peaks to be very narrow. So we want narrow peaks. I'll just write it over here. Narrow peaks. And we want good resolution. So spaced out. Peaks spaced. There we go. So that's kind of a summary of what we're looking for with our peaks.